Hi friends, let's have a quick view of chapter 13, Nuclei, second part. So from our last discussion, you noticed that nuclear force is the strongest force. Means it is stronger than Coulomb force of charges, and you know that Coulomb force of charges is greater than gravitational force of masses. So nuclear force is the strongest. Second thing, nuclear force between neutron-neutron, proton-proton, proton-neutron is same. Means nuclear force is independent of charges and no mathematical formula is required for nuclear force. And from graph, you can see that potential energy and distance means saturation force occurs when distance between two nuclei is more than few femtometer away. So now coming towards radioactivity, when Henry Becquerel illuminated iridium potassium sulfate plate with white light and wrapped them in black paper and separated it from photographic plate by a silver piece, and then photographic plate was developed. He observed some blackening and concluded that blackening was able to penetrate both paper and silver. So the rays, some kind of rays, is emitted from compound, and that phenomenon led to discovery of radioactivity. And it is also studied by radioactive decay. So let's see. The decay rate of a sample rather than number of radioactive nuclei is more direct experimental actually measurable quantity, and it is given specific name called activity, and the SI unit for activity is Becquerel, named after the discovery of radioactivity by Henry Becquerel. And now law of radioactive decay. Suppose there are n number of nuclei which undergoes decay. So after delta t time, there will be delta n nuclei will be remaining. So delta n by delta t is called rate of the nuclei undergoing decay. So delta n by delta t is directly proportional to n, means number of nuclei is more, then decay rate will be more. So it is directly proportional. And if we remove proportionality sign, there will be constant, and it is called lambda. So lambda is called decay constant or disintegration constant. And the change in number of nuclei is dn is equal to minus delta n, because we are talking about decay. So equation 1 becomes dn by dt is equal to minus lambda n. And if we take n to the left side, our equation will become dn by n is equal to minus lambda dt. And if you haven't studied integration in 11th or 12th, just remember the formula that if we are considering 1 by x dx, then integration of 1 by x dx will be equal to log x. And after that we have to put limits. Here our limit is n and n0. So first we will take n, and after that we will take n0, means log n minus log n0. That will be our answer for dn by n integration. So now again applying the formula of integration, that integration dx is equal to x. So here we are having integration dt, so then answer will be t, and we are going to put limit t minus t0. So final our answer is log n minus log n0 is equal to minus lambda t minus t0. That is our equation number 4. And now again applying the formula of logarithm, log x minus log y is equal to log x upon y. So now our equation 4 will become log n by n0 is equal to minus lambda t. And again applying the formula of logarithm, we will get n by n0 is equal to e raised to minus lambda t. If we want to remove log, then we will get such type of equation that log n by n0 is equal to e raised to minus lambda t, because base of log is e. So our final equation will be n is equal to n0 e raised to minus lambda t. And this is the change in number of nuclei. Now we are going to study total decay rate. So similarly we can find total decay rate is equal to R is equal to R0 e raised to minus lambda t. And just now we have proved that n0 e raised to minus lambda t is equal to n. So we find R is equal to lambda n. And this is total decay rate R. Now you can easily remember that the change in number of nuclei is equal to n0 e raised to minus lambda t. In total decay rate is R is equal to lambda n. Different radionuclei differ greatly in radioactive decay. So we are going to study half-life of a radioactive nuclei for our convention, and it is denoted by T half. And at T half, number of nuclei n will become n0 by 2. So T half is equal to, putting the value n0 by 2 in n is equal to n0 e raised to minus lambda t, what will you get? n0 will be cancelled, so 1 by 2 is equal to e raised to minus lambda t. And again we will use logarithm formula, and if you haven't studied, please remember the rules and formula, that if we take log on both the sides, left side we get log 2 and right side log a to the base e will be equal to 1. So our answer will be log 2 by lambda, and log 2 is equal to 0.693. So T half is equal to 0.693 by lambda, and mean life of a radionuclei is equal to RT delta T, and we substitute the value of R is equal to lambda n0 and delta T e raised to minus lambda t, and integrating both the sides we will get T is equal to 1 by lambda, and T half is equal to T log 2, means mean life multiplied by log 2. There are three types of decay: alpha decay, beta decay and gamma decay. Uranium-238 is converted into thorium and emitting helium nuclei is the example of alpha decay. In alpha decay, helium nuclei is emitted. So mass number of product nucleus, means daughter nucleus, is 4 less than that of parent nucleus. So general formula will be X A to Z will be converted to Y A minus 4 A minus 2 plus 2He4. So this is the general formula. Now disintegration energy or Q value of nuclear reaction. It is the difference between initial energy and total mass energy. And it is according to formula E is equal to mc square mx minus my plus mhe c square is equal to mx minus my minus mhe c square. So Q is the disintegration energy and net kinetic energy gained in process, or if initial nucleus is at rest, then kinetic energy of products. So disintegration energy and net kinetic energy is very important thing. And Q is greater than 0 for exothermic process like alpha decay. Now coming towards beta decay, in which nucleus spontaneously emit either electron or positron decay. Beta plus decay, neutrino is generated, and in beta and minus decay, antineutrino is generated. Neutrino is a neutral particle and can penetrate large matter quantity without any interaction. In both beta minus and beta plus decay, the mass number A remains unchanged. In beta minus decay, the atomic number Z of nuclei goes up by 1, while in beta plus decay goes down by 1. So the basic nuclear process underlying beta minus decay is the conversion of neutron to proton, while for beta plus decay, it is the conversion of proton to neutron. To understand gamma decay, you must know that nucleus has discrete energy levels like atoms, ground state to excited states. But order of energy is different. Atomic energy is of level electron volt and nuclear energy is of MeV. So when nucleus spontaneously decays to ground state from excited state, it emits photon. And this type of decay is called gamma decay. And the energy of that photon is equal to the difference of two energy levels of nucleus. When alpha or beta decay occurs and daughter nuclei is in excited state, then only gamma decay happens. And when in excited state to ground state alpha or beta decay occurs, then one or more than photon transition takes place. For example, nickel to cobalt decay. In previous lecture, we have discussed nuclear energy, and binding energy of nucleus is lower for lighter nuclei as well as binding energy is lower for heavier nuclei also. Means A less than 30 atomic number nuclei is also having binding energy lower, and A greater than 170 atomic number nuclei also has lower binding energy. So finally what happens that nuclei having less binding energy transform into nuclei having higher or greater binding energy. And in this process energy is released. So if two lighter nuclei fuse together to form one heavy nucleus, energy will be released. Similarly, heavy nucleus splits into two or more mass fragments, energy will be released. And this energy is called nuclear fission. And if two lighter nuclei fuse together to form heavy nucleus, then energy will be released, and this energy is called nuclear fusion. So disintegration energy first appear as a Ke, means kinetic energy of neutron and fragments, and then transforms into heat. In nuclear fission process, 2.5 neutron is released. Means in some fission process there are 2 neutrons, and in some fission process there are 3 neutrons. So we are taking on an average 2.5 neutrons are released, and we can get steady energy if we control this chain reaction, and in nuclear reactor this principle is used. And you know that U-238 is non-fissionable, but when it captures neutron, it produces highly radioactive substance plutonium through this process. Plutonium undergoes fission with slow neutrons. Enriched uranium U-235 is used as fuel. Now remember the role of coolant, reflector, control rods, and water condenser. So first of all, moderator. What is moderator? Moderator means in reactor, light nuclei provided with fissionable nuclei for slowing down fast neutrons are called moderators. And examples are water, heavy water, and graphite. And K is equal to multiplication factor, and it is the ratio of number of fission produced by given generation of neutron to number of fission produced by preceding generation. So if K is equal to 1, then the reactor operation is critical. And if K is greater than 1, then the reaction rate and reactor power increases exponentially. And reaction rate is also controlled by control rods, which is made out of neutron absorbing material such as cadmium. Safety rods are provided to reduce K rapidly. When more abundant uranium 238 captures neutron, it undergoes fission reaction and produces highly radioactive plutonium. So in reactor, reflectors are also used to reduce leakage, and coolants are used to remove heat energy released during fusion. Now let's see nuclear fusion energy generation in stars. Look at the reactions. 1H1 plus 1H1 is equal to 1H2 plus E plus neutrino plus 0.42 MeV, where E plus is positron. So in first reaction, two protons combine to form deuteron. In second reaction, two deuteron combines to form light isotope of helium. And in third reaction, two deuteron combines to form triton and proton. To experience nuclear force, two nuclei must come closer. But what happens that when they come closer, they are positively charged particles, so they experience force of repulsion, Coulomb force of repulsion, so they must overcome this barrier. And to overcome that Coulomb barrier, we know that barrier height depends on charges and radii of two interacting nuclei. So we have to provide T is equal to 3 into 10 raised to 9 K energy. So Coulomb barrier will be overcome. So when fusion is achieved by raising temperature, it is called thermonuclear fusion, and particles have enough kinetic energy to overcome Coulomb barrier in this process. A natural thermonuclear fusion process in star can be replicated in controlled thermonuclear fusion process, and its aim is to generate steady power by heating nuclear fuel to range 10 K, and at this range fuel is a mixture of positive ion and electrons. And the biggest challenge is to confine this plasma. Several countries, including India, are developing such techniques so we can have unlimited power supply. So friends, this all for this chapter, and wish you all the best for exam, and thank you for watching my video. Please like, share and subscribe.